Hello, good morning. In this webinar, we will see our design optimization of a cable arch bridge. This is me. I am Guglielmo Matacena. I'm a structural and geotechnical engineer. I am Italian and I had my master degree in Naples at University Federico II. I am a CNI member, the Italian Association of Engineers, but I work in Romania since 2019. Now I am in Aegis, Romania, where my focus is mainly on bridge structures. The Aegis Group is an international consulting company that is active in Romania since 1996. It has more than 19,000 of employees and design and supervise key infrastructure projects all over the world. Its expertise is focused on roads, rails, water buildings, and many more. Here is an overview of what we will talk about in this webinar. We will have a general overview on arch bridges, in particular on the network arch typology. Then we will see a little bit of our optimization project with a general description. Then we will see some 2D models that we have done to find the best strategy to optimize this bridge. We will see a little bit of modeling in civil next with geometry, in particular the modeling of the joints that are a very important part of this bridge. The cable pretension tuning, the moving load analysis, the buckling analysis, and then we will see some geotechnics with our seismic analysis in MIDAS, GTS, and X. The arc shape has been used since the ancient times as an intelligent way of distribute the vertical loads of a structure. This type of structure is perfect for materials that work only in compression at the price of increasing horizontal reactions on the supports. Then, with the development of metallic materials, tie element has been added to the arches in the lower part to take these horizontal forces and transform it in tension forces of the member. The modern arch bridges, you can see an example on the right, are based on the same concept with the addition of these hangers that allow to reach spans up to 600 meters. From the hangers layout as past the most part of the development of this technology. Here we can see some common layout. From left to right, we have arch bridge with vertical hangers. In the middle, Nielsen type with these inclined rigid elements. And then in the 50s, Norwegian engineer developed developed the idea of this new type of bridge with the hangers that crossed each other at least 2 times. This is the general rule. And this presents some advantages, as we will see. First, you have mainly axial forces in the element, so you can have smaller sections and more slender bridges. Like, for example, what you see on the right with this unpronounceable name is the most slender bridge in the world of this shape, obviously, of the arch bridges. Then you have a better redistribution of forces for uneven loads that we know that are very common on bridges, the traffic load in particular, and a better behavior in case of failure of some of the cables. Um, yeah, okay, our case study is a bridge. Sorry, is a bridge in the context of a roadway project in the zone of Cluj-Napoca. The structure consists in two symmetric arcs incline of 17 degrees with a span length of 250 meters, maximum height of 35 meters. We have in the feasibility study solution 2 rows of 40 cables with only one crossing point, a curved carriageway, all of variable sections for the tie beam and the arch, composite deck, and pile foundation. As we anticipated, this is a B design, so our scope was to improve the solutions proposed in the feasibility study and optimize it. To do that, we focused mainly on three main topics. The cable layout, so we studied the possibility to use the network type solution. The shape of the arch, since we used two different radius for the central zone, the main arch, and for the two lateral part of the arch to improve the distribution of the loads. In particular, the main arch has a radius of 210 meters, while the two lateral arch has a radius of half, I mean 105 meters. And another possible optimization was to improve the steel class, since from NS 355 to NS 460, since this type of bridge optimize the use of the material. I mean, you don't have a lot of bending moments, you have a lot of axial forces, so the inertia is not so important as it is for other type of bridges, and you can use better material to have a big improvement in the on the weight, a big reduction of the weight. So, as we said, to decide the cable layout, I compare some 2D models. We have three 2D models in particular. The first with 46 fingers, with a total length of the cables of 1,100 on a vertical configuration. Then we have a second one with 44 fingers with one crossing point. This is the feasibility study solution with about 1,200 meters of cables. And then the network arch solution with 42 fingers with a total length of 1,300 meters with 1 to 5 crossing point. Then on these three 2D models, we applied four loading conditions, an F-span constant load, a uniform distributed load, the self-weight, and constant predation load on the cables. And finally, we investigated the displacements, the bending moments, and forces in the cable to compare the results between the three models. So, this is a little bit of results. What do we see here? We have these are the displacements for the full loading condition. From the up left, we have the middle span load. Then we have on the right the uniform load on on the wall bridge. Then self weight and cable pretension. And what we can see here is that the biggest savings are on the half load span, the better savings for our network solution. We have on the half load span with up to 90% less vertical displacements. And we can also see from the fourth picture that we have the cables have a bigger influence on the displacements, so we can tune the cables to reach the result we need in terms of displacement. These are the bending moments. We can see a big effect also on the uniform distributed load in this case. Uh, and then we have the cable forces. The cable forces on average are bigger in the configuration of with the network arch. So another problem we thought about it was the modeling of the hangers as cables or trusses. The cable, what is the difference? It's a different way to model an element. The truss is an element that react only to tension and compression, while the cables is the same, but its stiffness varies with the stress. We didn't expect big difference because we don't have great sag effects. I mean the deformation of the cable that is not tense in tension. And this has been confirmed by our comparisons. On the upper part, you can see the hangers modeled as a tensional truss element, while in the three pictures below, you can see the results for the hangers modeled as cable elements. Um, uh, Also for bending moments, we have done the same comparison. The results are very similar. And these are the cable forces for both the element type. Okay, let's see a little bit how we model it in MIDAS Civil and next. Um, since we decide the cable layout with the network arch configuration, we um, we have some changes from the feasibility study solution. In particular, we will have two rows of 42 hangers with 1 to 5 crossing point. And we have an increase of the steel class from S355 to S460. The section used are box build-up steel section and I for the tie beam and the arch, and I composite sections for the transversal beams. These are all variable section, and to realize that in MIDAS you can create a tapered group that allows to automatically consider the interpolation of the height of the section over the length of the element. And another important part of the modeling is the modeling of the joint arc tie. This is originally made with the line elements, but we want to investigate the real behavior from the stress point of view and more precise buckling output, as we will see, since we will model also the plates and the stiffeners. So we want to convert this complex zone in plate elements that can be modeled in a more detailed way. So we created an Excel tool that calculates the vectors and generate the TXT files with the plate element data to be generated that then can be input in the MCT command shell. The MCT command shell is a very convenient way to interact with MIDAS. It's a tool that practically reads some text files and convert it in commands in MIDAS. What you see here is the plate elements that are created. Um, Here you can see what can you obtain with this tool. We will see a little bit how we model this complex part of this bridge very easily with MIDAS. So. So this is the structure we want to analyze. We will do an example for this zone, this corner zone between the arch and the type beam. The first thing we need is to export the nodes table and the element tables of the whole model. Here is the interface of the Excel tool we created. In this page, you can define the geometries and nodes you want to create. And here you can import, copy paste practically, copy pasting the nodes coordinates from the tables of MIDAS. The same for the element table. Remember that you can interact very easily with Excel in general with MIDAS Civil Next because all the information of the data of the model are in tabular form. So we just can do a copy paste in this case. And uh, going back to model, we can choose the element to convert in plate elements, which we start from the type beam. We select the elements we are interested to deep in the next page. So we just copy the IDs and we paste it here. Just three elements. It's a straight element in this case. We need to now we need the sections of of, uh, of these elements. The section information we need are in the calculation results. We need the center. We need the four distances of the coordinates of the four extreme nodes. We paste it here directly. We need the offset information now. You can find it here. In this case, we have a center offset. Let's give a check. Because yes, centroid, center, perfect. So we update the information here. Center, 0 vertical, 0 horizontal, centroid. Perfect. And the next step is to define the dimensions of the parts of the girder, of the steel girder. We have in this case one upper flange, one lower flange, and two webs. Okay, because it's a hollow section. This is the base. We have 1528 plus the 2 times the thickness of the webs. And here is the thickness of the flange, 550. Again, the lower flange is same of the upper flange. And this is the web information. We have 2.4 meters in this case. And we have to add 50 for the thickness. Okay. Then we have to choose from where to start to create the new nodes and new elements. So we see the last node and the last element ID in the list. And we don't want to create duplicate elements. So we choose a bigger number for the new elements that will be created. We choose the material ID and we choose the first free thickness ID that is free, in this case 2 and 5. And we can generate the code. The generation is the document is a doc Word file practically that's generated with all the information of coordinates and information of the elements and the nodes created. We just copy and we paste it in the MCT command shell. This is an example of 1 million and how you can use this precious function of MIDAS Civil. Because with this tool you can do what you can create whatever you want just text files. So you just need to study a little bit how it works, but it's very intuitive. And the elements are created, as you can see. We have now these are plate elements. We Let's give a check of the result because we want to check that it's all okay. Test, okay. Okay, as you can see, the shape of the plate element fits quite good the existing beam element. We are okay with this result. Here we are. Then, okay, this is done. We can pass to the arch, the base of the arch. We just activate all the elements. Okay, now we go in the base of the arch. In this case, we have four elements to convert. We just select it again because we want the IDs of these elements. We copy. Okay, and we can paste it again in that cell. In this case, we have curved elements. So intermediate rigid links are necessary to keep together the linear elements that compose the curve. Okay, now we need section properties. No, it's not this one. This one is the arch. We need the base of the arc section. We just choose properties. Yes, we check that it's this one. Properties. Okay. Now again, we check the offset of the section. Also in this case, is center as before. Everything is centered, so we don't need to change anything here. We need the calculation result. We select and copy paste in the cells. We work a lot with this MCT common shell function. We have done also other tools that automate a little bit the procedures. Here we have the dimensions of the elements. 2 plus 2 times 74, okay. Again, we change the thicknesses. Okay, DH is 2.34 plus the thickness. No, in this case, the thickness is not 50. Okay. We can input now the thickness of the web. Starting node, the starting element, we want to be sure that we don't create duplicate elements. Again, the same with the thicknesses. The materiality is always 5. So we need to close the older version. We can generate a new code with new coordinates and of the nodes and of the elements of this of the base of the arch. Okay, just copy and again MCT common shell. Okay, paste, run. Okay. As you can see, we have no errors. Don't worry about the warnings. It's normal because rigid link data is changed. It's okay. We expect that. So these are the rigid link we talked about. They keep together central node of the frame element with the new nodes created on the extremes of the section. And our objective now is to eliminate the rigid link that are not needed because we can connect directly the nodes together. Here you can see, for example, between the curved elements, these duplicate nodes. How we can do that? We can use the merge nodes function. You have a lot of tools in MIDAS Civil and Next for modeling. It's very good in this. We will use the merge nodes function with a tolerance of 0.1 meter because we are sure we don't do any damage this way because we don't have other nodes with a distance lesser than 0.1. We can select effectively everything without risk anything. Okay, and here we are. Apply. Now we have the nodes connected together directly without any rigid link need. Uh, Same for the lower part. We don't have duplicate element in this way. Now we want to improve the shape because we don't want these compenetrating elements, for example, in the zone of superimposition between the type beam and the base of the arch. So we can use the translate nodes function and the project nodes. In this case, we can see move. We can just select the node and choose the vector we want to connect. It's very intuitive, this operation in MIDAS Civil NX, because you can solve it also graphically, practically, just clicking on the elements you want to move. Again, for the third node of the type beam, we are connecting the type beam to the base of the arch. We start from this, then we need some intermediate nodes in the type beam because to connect the central node of the arch section. Frame, so planar, okay, we just divide in the x direction into. Okay, you can do this in very different ways. Just a possible procedure. Again, we translate nodes from here to here, and the same for the other one. Okay, and then we have to move the three bottom nodes to the first three nodes of the type beam, or the last element of the type beam. Okay. Here we have a problem because the geometry is not correct of the element that is generated. This is because we want to evitate, we need to avoid concave shapes and self-compenetrating elements. So we need to move forward these three nodes in the direction of the three nodes we want to move. We can try, for example, along the exact in an arbitrary vector. I mean the line already existing with a distance maybe of 0.5. We can try. So let's check if it's enough. So it's nodes here. Okay, it's not enough. So we need again to move a little bit forward that nodes. We think already set it. We just select the lower nodes. Sorry. Okay. So now should be enough. We select the three nodes, equal distance, and it's okay. Perfect. Now we have to connect also the other two remaining nodes. Okay, this is the first one, and this is the second one. Okay, so the first step is done. Now we want to use the edit nodes project function, project nodes. Practically, you can connect, you can project the central node on the line of the two extreme nodes. In this case, okay, we have to do not copy but move. Okay, in this way we have aligned nodes mm, that are more realistic, obviously. The same for the remaining nodes. Okay. And okay, these are the final nodes. Okay, in this case, we will project. Okay, this is projecting on a line. We have this strange shape of the plate element. So we can use the same function, project nodes, but using a plane as a reference. Okay, the plane with these three nodes and the direction vector of the existing line, the existing connecting line. The same also for the other one, the other node. Plane is this one because we don't want out of plane nodes. Okay, we connect this one. Perfect. Okay, now the shape, the final shape is completed. We have all element connected with just one node and not 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 wrong shapes. Okay, now let's see, we will have to do the last adjustments to this part. This is, as you can see, is very integrated in the structure now, but we still have these rigid links that we don't need practically. We need just external rigid links in the extreme parts to connect to the frame elements, and the one on the support on the nodes with supports. We can release slave nodes without specifying master nodes to make our life easier. And another thing we want to do is to delete the elements that are inside our plates elements because we don't want to have a double stiffness in these zones, and we don't need them because the elements are fully connected together. So we just select and we can just delete element. Everything is okay. Okay. So we in this zone we just have the planar elements. We can also obviously convert the other elements, for example, the transverse beams to create a more even realistic, even more realistic node between arc type beam and transversal beam. Sorry. So, what we obtain is this continuous shape of the arch. I said, we can create these stiffeners, steel plates, internal steel plates to reduce the free length of these elements that are very compressed. Some of them we will see. And for example, we can investigate now the stresses. For example, the axial stresses you can see on right. Here you can see in blue the compression and in red the tension, and we have a behavior that we expect from a structure of this kind. Then we have done with geometry. This is the final result. This is the bridge modeled in MIDAS Civil and Next. Then we start to talking about the traffic load. We use the LM1 from the Eurocodes because the LM2 in particular is important only for very short bridges. In general, is negligible. We have here the carriageway information. We have a total width of 23 meters, 4 lanes with a curvature radius of 1,500 meters, and a cycle lane outside the curve of 3 meters. Uh, we know that this traffic is a moving load because you don't have a fixed, this LM1 in particular, you don't have a fixed position of this load. You have to find the worst position that maximize its effect on each element. So to do that, MIDAS Civil NX has a very important function that is the moving load optimization function, where practically you can define carriageway and it automatically create a load configuration that maximized one particular effect for one particular element. So, for example, in this case, we want to maximize the axial force in the key element with the moving trace, and we can see the result of the moving load optimization analysis. And as we can see, we maximized to maximize the axial force on the K element of the arch. We have all the loads concentrated on the right part of the bridge, as you can see in this frontal view, and in the middle of the span, as you can see from the other two views. Now we want to know the pretension to assign to these cables. To do that, we have two tools. We have the unknown load factor and cable force tuning. To start to tune, we start with a pretension load of 1 kilonewton on each cable. So we create practically 21 static loads. We have 42 cables, but we create groups. We have two rows of 42 cables, but we want to this load to be symmetric on the four in groups of four to respect this symmetry. So we have 25 static loads. Then we go to bridge specialization here in results, and we choose unknown load factor. This you can do this after running an analysis. This unknown load factor allow us to iterate the calculation varying the forces in the cables to obtain a particular result. For example, in our case, our constraint, we choose as constraint the vertical displacement to be 0 at the node 626. That is practically under the center of the carriageway. We want to be 0. We want the displacement to be 0. So the program practically executes its iteration and then export the result as a load combination. Here we can see the unknown load factor result with the press stress force in each cable recalculated. Then on the right you can see the load combination export with practically the load remains one, but when we when we post process, we have this load combination with all the pre-stressed load applied as we calculated. Another function is the cable force tuning, when you can manually modify the pretension values and see real time the changing in the results. There we have two reasons why we want to tune again the forces in the cable after using the unknown load factor. The first is to meet our performance requirements. For example, we want to adjust the bending moments or I don't know, the displacement. Obviously, you cannot assign an infinite number of constraints when you use the non-load factor, so you can need maybe you need to work a little bit on details to meet other requirements. Another reason to use to tune again these cables is to round our values of pre-stress, because we cannot say to who built the bridge to apply a pre-stress of 180.9667 and so on. So you need to use more, for example, more rounded values. Then again, you can export as a load combination. You can update your load combination, and you can use it for the checks. Here we have a demonstration of the unknown load factor of the constraint we assigned. As we can see in light blue, we have the zero displacement. And under the node 626, under the center of the carriageway with permanent loads, we have exactly zero displacement as we asked. Here you can see some results for the ULS combination. These are the bending moments and the bending moment diagram. Here you have the axial forces. As you can see, we have a very big compression, as we expect on a structure of this kind. And in this particular, in the arch zone with this big compression, we can have a problem with buckling. So we want to analyze this problem. This is also the reason why we created this plate elements. The buckling analysis cannot be executed together with the moving load analysis. This is because the moving load analysis creates envelopes that cannot be analyzed in a buckling analysis. So we need to convert the LM1 position that maximize the axial force in the element we want to analyze for buckling in a static load. So we go in the moving tracer function, and we write the minimum maximum load to a file. The file is an MCT file, so practically always a text file, practically, that we can copy and paste this load in the MCT command shell to create the static load, as you can see on the right. So this moving load is converted to a beam load in this case. Okay, then in a nonlinear analysis, the superimposition of effects is not valid. So we create a load case from a load combination for the ULS combination in particular. Um, in the buckling analysis, we had the permanent combination and traffic load that we converted in a static as a variable action, because on the right you can see the buckling analysis from window where you have to assign a load to analyze practically. Here we assign the permanent load with a factor of 1 and the traffic load with a factor of 1.35. Okay, so For the backlink analysis, we also have to convert our tension-only elements in practice as a linear elements. In the operation, we lose our press stress load of 1 kilonewton we applied, but again we can use we can export this load in a MCT file, and again copying and pasting in MCT command shell. You can have again, as you can see on the right, all our loads applied again with no effort. So let's see a little bit of result of this backlink analysis. As we can see, already the first mode is a global one, and there's a critical load factor that is less than 1. Uh, what is this critical load factor? Practically is the multiplier you have to apply to the backlink load we choose before to reach the crisis of the element. If this value is lesser than 1, the linear backlink check is not satisfied. As we can see in this case, for the first mode, we have a critical load factor of 0.9. So, to resolve this problem, we have to add these cross elements on the upper part of the arch to increase the stiffness in this zone. So again, after creating these elements, we can run again the backlink analysis, and here we can see some results. Now it's very interesting because the first mode is a local crisis in the joint zone. You can see here in the detail with a critical load factor of 7. Consider that we could never catch this result if we did not model the zone with the plate elements. Again, in mode 7, we have a crisis in this plate element at the intersection between the arch and tie with a critical load factor of 20. Yeah, here. And then consider that usually a linear backlink analysis, going further with the modes, we have a bigger critical load factors. So this is the first. And then at mode 8, we have the first global mode shape with a critical load factor of 21. That is far bigger than 1. So we have a enormous improvement adding just these inclined elements. But remember that linear backlink analysis is what we have done, does not consider non-linearities by definition. So these non-linearities are not negligible and are also not on the safe side. We should consider also, and with MIDAS, with the civil Linux, we can do that. We should consider second order effects, I mean nonlinear geometries, nonlinear material, so the effect of the yielding of the material and the imperfections. Linear bugging is unconservative, but we have to consider that our model was created for a bit design. It's not a detailed design, so you don't need to go so in deep with the analysis. We have a critical load factor that is very high, so practically we have quite a big margin with our critical load factor. So we stopped to this level with a level of detail of the backlink analysis. But if you have to do a detailed design, well, these are very important aspects to take into account. Okay, finally, we want to investigate the soil structure interaction and the seismic behavior of the structure. So we imported the model in GTS NX because MIDAS Civil and GTS NX can communicate very efficiently. The Aero Code 8, the first thing to do is to import some loads to convert it in static load. This because the Aero Code 8 requires that for road bridges with severe traffic, the uniform distributed load and the seismic mass of traffic has to be considered, but reduced with a factor of zero point 0.2. So we create practically a personalized moving load and we convert it in static. And on the left, you can see the classic window when you define the vehicle. And here we just replace the psi factors to accommodate our need. We convert again as we see as we saw in the moving tracer static load to maximize the support reaction in the node, and in this way we can check the infrastructure. So we just have to export the civil NX file in a txt file and import it again in MIDAS GTS NX. The compatibility between the two programs is very high. Yes, GTS NX does not support moving load analysis, obviously, but converting this moving load, this static load, you should have no practically issues of communication between the two programs. We create the soil. The first thing to do is to define the surface. We use the terrain geometry maker is a function included already in GTS NX, and this from a 3D polyline we had already from a topographic study. We imported this 3D polyline and this tool interpolate a surface that is exported then directly in MIDAS GTS NX. Then we have on the left, you can see all the surfaces we create to simulate the layers. These surfaces are used to cut a solid block that constitutes our soil. The piles of our abutment are modeled as embedded beams. These are elements that does not need to be connected with the existing mesh through the nodes because we have to immerse a 1D element in a 3D mesh, and this it will be very hard to match all the nodes together. So this is a very convenient function to create this kind of embedded element. Here you can see the geometry completed. Then we can create the size control to mesh the nodes of the superstructure with the feature mesh of the soil. And here you can see the result. As you can see, you can create also hybrid meshes. Usually the meshes in 3D FEM programs are tetrahedral. With these hybrid meshes, you have also quadrilateral elements that are more accurate, more stable. As a boundary condition, well, our objective is to execute a construction stage analysis for the static loads and combine it with the result of response spectrum analysis. So we create two boundary conditions, ground surface spring for the static analysis and free field boundary condition for the seismic one. Practically here you can see the application of the ground surface spring where you have to input just this one coefficient that depends on the way you obtain the elasticity of the soil, the modulus of subocrate reaction. Here you can see the free field settings. Practically, the free field, the ground surface spring simulate the external boundary with the springs corresponding to the adjacent soil characteristics, while the free field simulate an infinite soil mesh to allow you to limit the dimension of the model that can be very hard to run on your computer. Practically, you can create a smaller surface and simulate an infinite extension of it with this width factor. You can also apply dampers in case of time history analysis. But we will execute a response spectrum analysis. So these are the parameters we use from the Romanian codes. This is a low seismicity area with a peak ground acceleration of 0.1 g and period TC of 0.7 seconds. And but MIDAS GTS NX has already a wide design spectrum database included the P100, the Romanian seismic code. So we compare the spatial traffic load we created in civil in masses through the function load to mass. And practically the result is the creation of a new mesh that will enter in the calculation and accelerate, but that will be multiplied by the acceleration we will apply. Then we will execute two response spectrum analysis in the two directions and two construction stages analysis, one for geo and strength checks and one for the seismic combination. For the response spectrum, we use CQC analysis, CQC combination, and we consider up to 300 modes to reach the limit of 90% of participant masses. Remember that when you execute a construction stage analysis, you probably will need to create an intermediate first step, that is the geostatic stress state, where you clear the displacement. This is to visualize only the displacements that are created after the application of a load. And then we activate the permanent loads and finally the traffic. Here we can see some displacements of the soil and of the infrastructure. Then on the right, you can see the shell forces in the abutment. In this way, we can also check the concrete structure. Here we can observe the results of the response spectrum analysis with on the left the model combination in the x direction. Here you can see also the behavior of the free field boundary condition, since the boundaries are free to move, and the first model in the y direction. So we can observe if the results are okay, seems correct. And finally, we can create our seismic combination. We can combine in GTS NX the single analysis results and applying scale factors. Practically, you are creating a load combination with the whole analysis. So a new group of results is created, is here on the left in the free menu. And from here, for example, we can see the shell forces in the joints of the arch we created. So Our optimized solution allows us to save up to 25% of steel in terms of weight, which 35% for the S355 type steel and the 65% for the S460. No significant changes in steel weights for the cable, small savings for the metallic surfaces to be painted, but thanks to the changing of the configuration with the cross beams for added for the buckling, we have an increased safety in this context. All of this information can be obtained thanks to the below material function in MIDAS Civil Annex that shows all the weights, volumes, and surfaces of all the elements that are modeled directly in the software. So this was the last slide. Thanks for attending the webinar. For any question, you can send an email to the email addresses you find in the lower part of the slide. Thank you so much.